To introduce our speaker today, Dr. Roger Wakamoto, very world-renowned scientist. We're really glad that he's going to speak with us today. Currently the Vice Chancellor for Research and Creative Activities at UCLA, and he's done a lot of atmospheric research, specializing in mesoscale meteorology, especially convective storms and radar meteorology, which is the subject of his talk today. Roger's actually held a lot of distinguished positions, including being the director of NCAR and also assistant director at NSF, and also president of the AMS for a couple of terms not too long ago. And we'll look forward to hearing his talk. So welcome, Roger, and we'll turn it over to you.
Well, thank you very much, Ralph. And it's been a while since I've been at the University of Maryland. I wished I could be there in person, but it's great to have been invited. I thank John for the invitation. By the way, it's also great to talk about something I really like because my day job is all-consuming. So to talk about research is very relaxing to me. So I'm going to be talking about one of my favorite subjects, and that's tornadoes. And I really have two parts. One is talking about the lofted debris cloud that envelops the funnel. And the second part is to talk about cycloidal damage swaths at the surface that have often been revealed in post-storm surveys. I want to certainly acknowledge my contributors, Zach, Howie, and Dylan are University of Oklahoma, and Dave Lewellen is West Virginia University. So I never want to assume that the audience is well versed in this subject. So if you pardon me, I'll give just a little bit of background. First, the kinds of storms that produce the most powerful tornadoes are called the supercells. You may have heard that term. And they're characterized by this storm scale rotation that's at mid-level. We call it a mesocyclone, which is on the order of a few kilometers in diameter. And really the holy grail of tornado research is trying to figure out how do you get from the storm scale rotation down to the tornado, and the size of the tornado is about right. It's about an order of magnitude even smaller than that, than the mesocyclone. We still struggle with that. I'm not going to be talking about it today, but it's sort of the holy grail. Now, if you take a horizontal cross-section through this supercell and use a radar, going to introduce you to the first of four variables that I want to highlight in this talk. And I think you know this variable. That's echo, or what we call radar reflectivity. It's just telling you where the precipitation is. And that's outlined here in this horizontal cross-section in magenta. And if you look at the bottom left, you see that the magenta outline hooks around. And for that reason, we call it a hook echo. And it's an indication of storm scale rotation. It's a very famous radar signature. Well, here's another depiction of a hook echo. I've shown this one because this actually shows up in a lot of textbooks. It was put together by Chuck Doswell and Les Lemon. And the only thing I want to highlight here is the red letter T. It is approximately, and I do mean very approximately, where you'd expect to see the tornado. Well, now let me introduce you to the second of the four variables that our radar measures. And that's Doppler velocities. And again, I think some of you are aware of this one. Let's just superimpose a cyclonic or counterclockwise rotation. Maybe it's the storm scale rotation, maybe it's the tornado rotation. But let me put it down there. I think you can see it. So what does a Doppler radar measure? It only measures the component of motion toward or away from the radar. It cannot measure the cross beam component. So for this circulation on the northeast side, it'll see velocities away from the radar. That's often color-coded in yellows, oranges, and reds, as it shows here on the schematic. On the southwest part, you see velocities toward the radar, and it's often color-coded in the greens, the blues, and the purples, again, as shown on the schematic. Now, down the middle, in between these two colors, it's zero velocities, and that's not because the air is stationary. It's because the motion of the air is perpendicular to the radar beam in it, so it measures zero velocity. So this is another famous radar signature. It's the rotational couplet, and often looked at by forecasters to warn of intense circulation. Just want to remind you that the way a Doppler velocity or Doppler radar works is no different than a police Doppler. Anytime a police officer is shooting that police Doppler at you, he or she must point it directly into the oncoming car. They point the gun at you when you're passing by, they should technically get zero velocity. Well, I'm always interested in some of the history. And one of the things I was always wondering is what was the first report of a hook echo? And it was in 1953. It's actually, if you go back and look at the archives, it's in Bulletin of the AMS. And you can see with the blue arrow, it really does look like a hook, like on a clothes hanger. I would argue that we didn't learn much more about hook echoes till 1981. Ted Fujita published this article where this is an enormous blowup or an enlargement of a hook echo. And he noted with the blue arrow this little hole, this weak echo hole, weak echo eye in the middle of the hook. If you look at the schematic on the right, it's actually showing you where the tornado is located. So you might ask, why should there be a weak echo eye where the tornado is? So I created this schematic to simply explain this. The blue represents the hook echo. And notice there's a weak echo region, the black center. And I labeled that WEH. And then the brown is the tornado. And then the red circles are hydrometers, precipitation particles. They could also be debris particles. So what's going on is the tornado is rotating so rapidly, it's essentially centrifuging out these particles, throwing the particles out. Well, the radar echo is based on scattering energy off these particles. Well, if there are no particles in the middle of the tornado, there's not going to be any echo. And so that's a simple explanation as to why you get this weak echo hole and why that shows you where the tornado is. Oh, very quickly, Josh Werman with his Doppler on wheels, or what is called the Dow, has for the last, nearly 20 years, hard to believe, has archived this steady stream of enormously magnified images of the hook echo, some of which have been jaw-dropping, and you can, here are just some examples. You notice they all have weak echo holes. This is now, we now know this is a very common feature of hook echoes, showing you where the tornado is located. So with that, now let me start transitioning into really this first part of my presentation, and that's debris. There's lofted debris that surrounds the funnel. On the upper left, it really is debris. And actually, if you study this image, they're actually huge debris, like buses and cars being lifted. This is a very powerful tornado. In the bottom right, this is more sand, dust being lofted by the tornado. Now, lofted debris is a common feature of many tornadoes, but actually little is known about the debris characteristics and its impact on the tornado dynamics. Now, I'm not going to be talking about its impact on tornado dynamics. There are other people that are looking at this. I'm looking more at the debris characteristics. These three images just show you that this lofted debris cloud comes in all kinds of shapes and sizes. In fact, in many cases, it's more spectacular than the tornado funnel itself. So all of the data that I'll be presenting in this seminar has been collected by a radar called RAXPOL. And that acronym stands for Rapidly Scanning X-band Polarimetric Radar. And let me just touch on all three aspects so you know what I'm talking about. So below, you see the wavelength is 3.1 centimeters, and that tells you about the X, because 3.1 centimeters is the X band in the electromagnetic spectrum. The beam width is 1 degree, which is fairly typical of radars. The azimuthal scan rate, though, is 180 degrees per second. I want to pause there because that means this radar can do a complete 360 in 2 seconds. That's the rapid scan part. And then the antenna is about 2.4 meters in diameter. So this is a typical volume scan. We might try to do 0 to 6 degrees elevation scan in 1 degree steps. So RAXPOL can do this in about 20 seconds. And in comparison, what would a regular radar be able to do if it didn't have rapid scan capability? It probably would take 2 to 2.5 minutes to complete this volume scan. So this is really a step up in the temporal resolution. We'd like to do even better than that, and we think we can, but 20 seconds isn't bad. So now let me introduce the third of the 4 variables, and this now gets into the pole part of RAXPOL, the polarimetric capability. And you may have heard of polarimetric radars, and I just want to, for those who are not familiar with it, show you some schematics to explain two of the variables. One is ZDR, or what we call the differential reflectivity. It's pretty simple, actually, schematically. You send the beam out horizontally polarized, you measure the return. You send the beam out vertically polarized, and you measure the return. You take the ratio of those two values with the horizontal return in the numerator, vertical return in the denominator. You take 10 log of that to get it in units of dB, and that's differential reflectivity. So now that you know that, what does it tell you? So this schematic illustrates what it tells you for precipitation particles or raindrops. We know that small raindrops are basically spherical. Well, if they're spherical, you should get the same return horizontally and vertically polarized. You take the ratio of that, that's 1, and then 10 log of 1 is 0. So if you know there's precipitation particles out there and your ZDR, or differential reflectivity, is 0, then you can be pretty much sure that it's small raindrops. But as raindrops get larger and larger, they become, the technical term is oblate spheroid. The non-technical term is they become frisbee-shaped. And you can see what happens. You'll get more return horizontally polarized than vertically polarized. And if you look at the top right, you start getting very large positive ZDRs. You can see in one example, a 4 millimeter drop. If they were all 4 millimeters, would start giving you ZDRs greater than 4 dB. So hopefully you got what ZDR is. I've talked about the first two lines here. Large drop give large positive ZDR. Small drops give low, sometimes near 0. I didn't talk about hail, and you might question why hail is low ZDR, because hail can be very non-spherical. But in convective storms, we know that hail tumbles like crazy, and in the tumbling process, it effectively looks like a sphere. So you get near 0 ZDR. And then for this presentation, what about debris? Well, debris, because debris comes in all kinds of shapes and sizes, it's tumbling like crazy too. You also get low ZDR in lofted debris. Something that we've noticed recently is increasing reports of negative ZDR in lofted debris. And that's caused a lot of people to sort of scratch their head and say, like, what's going on here? Why would we get negative ZDR in lofted debris? And so I was curious about this, so I'll come back to this later in the presentation. And the fourth and final variable that I want to introduce to you, it too is polarimetric, is the cross correlation coefficient, or ρHV. And it's actually pretty simple conceptually. It says take the horizontal polarized energy and correlate it statistically with the vertically polarized energy. So what does that buy you? Well, for example, if it's precipitation, precipitation particles tend to be very well ordered. And so when you do this correlation, you get a very high correlation coefficient of near 100%, or sometimes I say 1. Debris, again, because of all kinds of different shapes and sizes and it's tumbling, you get very low cross-correlation coefficient. So rather than describe it to you, let me just show you an example. This is a horizontal scan. Red on this scan of ρHV is near 1. And you probably could have guessed the purples, the blues, the yellows are much lower values of ρHV. And so in this horizontal scan, what I'm trying to show you is that I think you can see it. This approximately circular shape tells you exactly where the debris is located. And so it is a favorite variable to locate debris when it's being lofted by a tornado, because it just jumps out at you when you look at a screen. Vladimir Ryzhkov, a number of years ago, came up with what he called the TDS, or Tornadic Debris Signature. And very simply, I'm using the El Reno tornado, but I could have used other tornadoes. This is the characteristic of a TDS. On the top left, you get a hook echo with a weak echo hole, which the black arrow is showing you. On the top right, there's a prominent rotational couplet. Now, this is a real example. That should look like the schematic I showed you. By the way, that's a huge rotational couplet. The range rings are every 2 kilometers. This is gigantic. And the tornado was gigantic. In the bottom left, maybe not so well defined, but you see these areas of gray, green, purple, blue. That's relatively low ZDR. The yellows and reds are relatively large ZDRs, and that's actually, I can tell you, where raindrops are located. But you can see why we prefer to use ρHV. the location in this horizontal scanner where the debris is just jumps at you. You can even notice it. It doesn't take an expert. It's a great variable to use. So I love this picture. This was taken by Dylan Reef. Finally, after all these years of severe storm research, someone captured a picture of me taking a picture of actually the case that I'm going to talk to you about today. This is the Dodge City tornado. This is not Photoshop, by the way. I'm not being pasted into this photograph. It's a real photograph. And it allows me to introduce the subject of photogrammetry for those who are not familiar with it. So I have another schematic to try to explain it to you. I'm standing where the red star is, and in all the analysis I'll be showing you, I'm basically filming out to the west. There's Raxpol, and Raxpol and I are basically co-located. So you can just say, you can think of Raxpol also being where the red star is. And then I have a picture of a hook echo with a weak echo hole out to the west. And then I have schematically in there a photograph of a tornado. So photogrammetry is nothing more than a fancy word to say that I can actually put the elevation and azimuth angle grid on top of the picture. But because I'm actually standing at the same site as the radar, those elevation and azimuth angles actually represent the radar scanning angles. So then it's relatively easy to do a vertical cross section through the hook echo, through the hole, through the tornado, through the rotational couplet, and actually project that data on the picture. It allows you to interpret the picture in a much more quantitative way, which I always enjoy doing, rather than a very qualitative like, oh, there's a picture of a tornado, but you can't do much else with it. I like to take it to the next level. So let's start talking about the Dodge City tornado. This is the day, March 24, 2016. The circle represents where Dodge City is located. You see storms have already really developed pretty intensely. You can see the anvils. And that anvil over Dodge City, this picture actually was taken when tornadoes are already on the ground. Now I can tell you on this day, this is a picture I took. I was really nervous because you can see the first of the Dodge City tornadoes off to the left, and we're not in position. I think it's pretty obvious because there's Raxpol driving down the road. You can see spray being kicked up off the road, and I was frightened to death saying, oh my God, we're not going to get in position. That Murphy's Law is going to say that as soon as we get to the tornado, it's going to dissipate. Thank heaven I was wrong, but I was sweating at this period when I took this picture. And you can see one of the reasons why I didn't have to worry, because if you look at the top left, it says tornado number 4. There was a whole series of tornadoes that formed from this one supercell. So this is of tornado 4. This is just 3 illustrative of pictures. One when the funnel cloud is just forming on the top right, or top left, I should say. A little bit later when the Dodge City tornado is well formed. And now you can see some dust being kicked up at the lowest levels. And then the bottom left where you can see quite a bit of dust enveloping the funnel cloud. I think I'll skip the bottom right because you'll see another example of that later. One of the other things I should mention is those 3 images. In any image I show you, the images have either been enlarged or reduced, which I can do photogrammetrically, so that the relative dimensions of the funnel are the same. And you might ask, why do I do that? Well, if I'm taking pictures of a tornado and the funnel is getting larger with time, it could be because the tornado is getting larger with time. But there's actually another reason, and that reason is the tornado could be approaching the photographer. Well, by making this adjustment of enlarging or reducing the photograph, I negate that second part. So anytime in any of the pictures I show you, if the funnel looks bigger, it's because it really is getting bigger. Subtle thing, but important. Whenever there's a major tornado outbreak, I like to do a damage survey, and I do it both by air and the ground. And in this case, I used the Cessna 172, which this was the aircraft I used on the bottom right. You may be able to see the tornado track. If not, I'm going to highlight for you. Very fortunate. The Dodge City tornadoes basically occurred in open terrain. There was only one building, I think, that was unfortunately right in the path of one of the tornadoes and was totally destroyed. Most of the time, the tornadoes were going through dirt fields, wheat fields, and grass fields. This one really jumped out at me. It's one of the best examples I've ever taken of you can just see the track. in fact, now you can see the track, you can actually measure the width of the core of the tornado. It's 80 meters here. In fact, I was so fascinated by this portion of the track, I took an enlargement. So you can really see the details of this track. And if you look carefully, you now start seeing some of these cycloidal swath marks. And this will be the emphasis of the second part of my talk later on. And then the images are the same, both left and right. And all I've done on the right is highlight the tornado track. But I think you can see it on the left, so probably it wasn't worth me highlighting it. These are just illustrative examples of the tornadoes. A remarkable 10 tornadoes occurred from this one supercell. This is a little hard to see, so let me enlarge it on the right. You see Dodge City. Fortunately, all the tornadoes occurred west of Dodge City, and that's really fortunate. If these tornadoes have gone through Dodge City, I can't imagine how much destruction and how many people could have lost their lives. Notice Raxpol was set up at 2 sites, site number 1 and site number 2. All the data I'll be showing you today was based on data recorded at site 1. I'm going to highlight 2 tornadoes today. The first one is tornado 4, and I've just color coded it in red so you could see it a little bit better. But also notice I'll be showing you data later on from tornado 1. It's the tornado in the bottom left. Blue circles represent the location of the tornado at different times, as identified by the radar, because the radar sees the rotational couplet. And so that's how these timestamps were determined. Now, if you look really carefully at this damage survey, you'll see times that suggest that, gee, if I believe all these times, it suggests that more than one tornado must have been on the ground simultaneously. That happened several times, so let me show you the one at 2330. And sure enough, this is a picture I took where you see tornado 4 on the left, but you actually see tornado 5 on the right. It's not very common when you capture 2 tornadoes simultaneously, but that's why this case is so spectacular. You can also see I've done a photogrammetric analysis of this picture because you see the elevation and azimuth grid superimposed on the picture. You'll see other examples later on. So this is tornado 4. From the beginning of the track to about midway along the track. Again, it may be a little hard to see, so I'm just going to enlarge it for you. What's on this image or this map? Well, the brown lines and the dashed brown lines show you the different fields and the field characteristics. Now, I think this is really important because I'm talking about debris that's lofting. You better know what the debris is. And so you can see I've labeled wheat field, dirt field. So that's well documented, all based on the aerial survey. The red line represents the tornado track. The circles represent the location of the tornado, all time stamped. And I think the only other thing I want to mention is the blue arrow. That's going to be the first analysis. I'm pointing at the time and the location on the track where I'm doing the first analysis. So this is the time where the blue arrow was pointing, 23:30:33. This should look very much like that Vlad Richkoff TDS signature. You see the hook echo on the top left with a weak echo hole. You see on the top right another rotational couplet associated with this tornado. I'll skip the bottom right because that's ZDR, which is not as spectacular as the row HV on the bottom left, where there's the debris cloud. This is a horizontal scan at 1 degree. Now I'm going to add something, and it may be a little hard to see, but I'm adding a red circle on all these images. And what is it? It's the funnel diameter. And how did I determine the funnel diameter? I did it from the pictures. I did it photogrammetrically. And in fact, that's the only way to do it because the radar cannot tell you the funnel width. It doesn't have the capability of determining the funnel diameter. So that's why I have superimposed the red circle. I do that because I'm often curious about the size of the tornado funnel in relation to the signatures you see. For example, that's a tiny funnel compared to how much debris is being kicked up. The other thing is this brown and red ring here, which is area of higher echo or higher radar reflectivity. This has been hypothesized to be the debris ring. It's a ring of debris being kicked up by the tornado. And we'll come back to that a little later. So again, at this time, 2330, here is tornado 4. Again, I've performed a photogrammetric analysis. Because I'm at the radar site, it is then relatively easy to take a vertical cross-section right through the tornado and superimpose, in this case, echo or radar reflectivity. Blue shading is relatively weak echo. For those who are interested, that's less than 20 dBz, so that is weak. WEC means weak echo column. That just means the weak echo hole in the vertical we call a column. Anything that's not shaded means it's relatively higher echo. So perhaps not surprisingly, you see the tornado funnel centered right on this weak echo column. Notice this relatively higher echo intensity just outside the funnel. That's that debris ring I showed you in the previous slide, this donut-shaped configuration of high echo that surrounds the tornado. How about doing a vertical cross-section through the rotational couplet? And I first have to apologize because I shouldn't have used red and green. If you have color blindness, these are the worst colors I could have shown, so I apologize. For those who can see it, the green represents velocities away from the radar. The red represents velocities toward the radar. Shaded green is greater than 50 meters per second. Shaded red is greater than 50 meters per second. And so what you're seeing is the vertical structure of the rotational couplet superimposed on the funnel. And by the way, based on the way I've done this, the green literally represents velocities into the picture, and the red literally represents velocities out of the picture, which is actually the correct interpretation. You can start seeing why I like to do photogrammetry. And now, here's your very first look, and actually, as far as I know, the very first time this sort of image has been shown. This is rho HV. The shaded red is less than 0.4, so it's really low rho HV. Now, if you look at it sort of stepping back at this image, you see this column of low rho HV. One of the things I want to highlight is that, as shown here, you don't visually see debris, but the radar is telling you there is lofted debris because the rho HV values are dropping. So it shows you the power of a radar. But let's look very carefully at this column of rho HV. It's not as simple as you might imagine. From middle of the tornado up, the shaded area, which remember is the lowest values of rho HV, is centered on the tornado funnel. But below that, the lowest values of rho HV are actually off axis, off tornado axis. They're outside of the funnel. So why is that happening? So that's just what I said. The minimum at the surface are actually not centered on the tornado. It's actually a little relatively higher rho HV right where the funnel is. So let me, hope it's not too noisy, but I'm superimposing the echo that I showed you earlier on top of the rho HV column. And you'll notice that those two areas of low rho HV are also two areas of high radar reflectivity or high echo. What that suggests is those two areas are where debris is congregating, really high debris loading at that area. It's important because that has only been shown in numerical simulations. This is the first time observations have clearly shown this. So let me segue just for a couple minutes on numerical simulations. And to me, the most dramatic numerical simulations have been by Dave Lewellen. Here are some simulations that he has performed of a simulated tornado moving over a sand field and with time lofting more and more debris. I mean, his simulations are so spectacular that they really look incredibly realistic and mimic what we see in real tornadoes. Here's another example where he uses small debris particles on the right and larger debris particles on the left. Not surprisingly, the lofted debris cloud goes to higher levels when you have smaller particles. So using Lewellen simulations, what he did in his article was to take azimuthal averages of debris loading. And so this is a vertical cross-section, and the tornado is at 0, where I've got it labeled with the black arrow. That's the tornado center. And range away from the tornado. So this is, again, an azimuthal average. The blue lines are debris loading, as I said. The shaded blue is very large debris loading. And the only other thing to explain on this figure is the red shading, which is where the maximum rotational velocities are. And you notice the max debris loading is off the center of the axis. It's outside of the center of the tornado. So simulations have shown this too. And actually physically, this is pretty easy to understand. Remember I told you that tornadoes centrifuge debris from the middle of the tornado or the center of the tornado. But what happens is it eventually runs into the inflow, because not only is a tornado rotating, there's massive inflow spiraling into the tornado. Where those two collide is where you get debris starting to build up. And so that's what I showed you in the observations, and that's what Lewellen is also showing you in the simulations. So this is the same tornado, but just a couple minutes later, and now it's gotten quite large. And again, because I've done the photogrammetric analysis, I can tell you it's over a couple hundred meters in diameter. Dust is, at least visually, being lofted. Again, this is just sort of superimposing the cross-section through the tornado of echo. Shaded blue is less than 20 dBz. That's the weak echo region, again, centered on the tornado. Notice these relatively higher values of radar reflectivity or echo. In this time, that's the debris ring. But this time, notice it's pretty close to being smack on with the visual debris being kicked up at the lowest levels. Let me show it to you in a different way. This is a hook echo you've already seen. This is what I showed earlier. All I've done is rotated and enlarged it, and you'll understand while I rotate it in just a second. The black line represents the cross-section, the photogrammetric cross-section, and let me show you that now. So what have I done? One is I've lined up the viewing angles. This is 300 degrees, but this is also 300 degrees on the photo. So I've lined up the viewing angles. So you can think of yourself being down here, looking down 300 degrees. And the length scales are the same. So the length scale of that radar image, I've matched it to the photograph below at the distance of the tornado. So again, why am I doing this? Because this is literally how that tornado visually fits into that hook echo. That's the size of the funnel at this time, and you could literally displace it into the hook echo. Again, I'm always at least fascinated about how this relationship, how it looks visually and what the radar is seeing. Here's another vertical cross-section of rho HV. Shaded red, again, is less than 0.4, so that's the minimum of rho HV, and it's centered right on the tornado. But once again, I tell you to look, I ask you to focus in at low levels. The real lowest values of rho HV are off the center axis, actually just outside of the funnel. And also sort of encircling the dust debris that you see being lofted at low levels. Very nice when you see the picture and the radar data matching so well. And now your first image of ZDR. Again, I apologize for using green and red. I'll correct that in the future. But the green represents positive ZDR. Shaded green is greater than plus 3 dB. So I can just tell you straight out that those areas of shaded green are large raindrops. The red represents negative ZDR. The shaded red is less than minus 3 dB. And I think it jumps out at you. This negative ZDR that I mentioned at the beginning of my talk is very coherent. And in this case, just centered right on the tornado. And again, the question was, what is causing this? Where all this debris is being lofted, why are we getting this rather prominent negative ZDR column? So I'll just jump to the story. Turns out when I was doing this analysis, several people at the University of Oklahoma had created a polarimetric radar simulator. And it's just as the name says, they were simulating polarimetric data. In other words, what a radar might hypothetically see in this simulator. So this is a vertical cross-section, and you can think of the blue as the tornado funnel. And what they did in this simulation is they released debris. And the debris is all that red, but all that red is negative ZDR. So this polarimetric radar simulator actually replicated this negative ZDR. And what they showed in their simulation, this was because of common debris alignment. And the debris was lofted leaves. And so what does that mean? It means just like this schematic of lofted leaves in the bottom right shows, these leaves are primarily being oriented just the way you see in this picture, with their vertical axis up and down in the vertical. And so because of that, you're getting more return vertically polarized than you are horizontally polarized, and that would give you a negative ZDR. Again, this is somewhat fascinating. I wouldn't think that debris would orient this way in a common, in sort of a preferred way, but that's apparently what's happening. And so I'll jump to the schematic. There's a lot in the schematic, but I'm just going to highlight two things. You notice this little black box in the center of the funnel, which I'm enlarging in the top right. Not only am I showing red particles, which are debris, I've got all these little green lines. Those green lines are wheat stem, and I'm showing them in a preferred orientation, common debris alignment. And I'm almost convinced that's what's going on in this case with the Dodge City tornado. Why did I say wheat stems? Because remember, I did the damage survey. And during this time, as I show here on this aerial photograph, this tornado was going through wheat field after wheat field, in addition to going through dirt. So there's no question that wheat stems were being ripped out of the ground and being lofted. And so the only logical explanation is that these wheat stems were oriented as shown in the schematic. So that's that first bullet here that I'm talking about wheat stems that are vertically oriented. The other bullet, the second bullet, is what you can see down here, these two bullseyes where I've actually schematically drawn big particles. The observations clearly show this high debris loading that is occurring just outside the funnel. So hopefully you've learned a little bit more about lofted debris. There's more I could say, but I'd like to switch to the second part of my talk, and that's the cycloidal debris swaths. And I can't introduce this subject without first talking about Ted Fujita, famous tornado researcher. He was often referred to as Mr. Tornado for two reasons. One is because he contributed so much to tornado research, but he also, because it kind of describes, for those of you who knew him, it sort of describes his personality. He was just this whirlwind of activity. Just a few of the things. I mean, he accomplished so much in his career, but I wanted to highlight just a few things. One is he developed the F scale, the Fujita scale, for assessing damage intensity. Quite often misinterpreted as saying it's a wind scale. It's actually not a wind speed scale. It's a damage intensity scale. It's been modified. It's now called the EF scale, for enhanced Fujita scale. Actually, there's a story with that. If someone asked me a question at the end, I could tell you about. He discovered the microburst phenomena. At the time he discovered it, the microburst or wind shear events were causing numerous aircraft to literally fall out of the sky. I don't think it's an understatement to say that his research on the microburst saved thousands of lives because his research was fed into pilot training, improved pilot training. And for this talk, he really elevated damage surveys to just another level beyond what anybody else had done. And we learned so much from that. For example, even predating Fujita, it's been well documented that in the aftermath of tornadoes, when you fly over a damaged field, you'd often see these cycloidal debris swaths. And what can you learn from that? We can learn several things. As I even showed you earlier in the talk, the dashed white lines tell you how wide the tornado core is. Also, if you look at the cycloidal marks very carefully, and in this case, if you assume the tornado's rotating counterclockwise, it also tells you which way the tornado is moving. It can only be moving from left to right. It cannot be moving from right to left. Even if you don't see the tornado, you know this is what's going on. But to help you out, if you can't see it, these with the yellow lines, I'm highlighting these cycloidal marks. By the way, the non-technical term, the kids' game, what, spirograph? That circle with the hole, you put the pen in and it makes all these cycloidal marks. The analogy is correct because that's how these marks are created. Now, the prevailing theory, though, before Fujita became involved, is these were gouge marks. Essentially, tornadoes were picking up debris and just gouging these marks into the field. And it was Ted's very detailed damage surveys that actually came up with another scenario. On the left, you see aerial photographs of these cycloidal swaths. I've highlighted it in yellow with the bottom picture. It's the same picture, I just highlighted the swaths. And what Fujita did was he went down on the ground and said, well, wait a minute, these aren't gouge marks. This, in this example, these were corn stubble. He said what was happening here, corn stubble was being brought together, converging together through some suction process, highlighted schematically with the yellow line on the bottom. And so I'm saying here what, I'm writing here what I just said. These were not gouge marks, but debris being congregated or collected by a suction process. So what Ted said was, okay, and this is the way Ted's mind worked. I see these marks. I know they're not being created by gouge marks. He made a huge leap of faith and actually came up with this very famous schematic model. And I want to make sure you understand, he did this absent of any visual documentation of a tornado. He came up with his famous suction vortex model, which proposed that tornadoes broke down into these multiple secondary vortices, all rotating around a common core. So that was the first part of his schematic model. But there was a second part, that these suction vortices were creating these debris marks, these cycloidal suction debris deposit marks. For those who are familiar with the history here, I can tell you that when he proposed this, he received just an enormous amount of pushback from the severe storms community. And the reason should be obvious. It was, to my mind, historically incredible because people were taking pictures of tornadoes for decades and decades. But for whatever reason that I cannot explain, no one ever took a picture of a tornado that actually showed these multiple vortices. And so that's what his critics were saying. If these vortices exist, as you proposed in your schematic model, show me a picture. Well, he couldn't. And so this was all the criticism that he took at the time. However, I think you know the end of the story, that about the mid-70s to much later, suddenly there was a slew of documentation that showed that this multiple vortex phenomena does in fact occur, certainly in the video and even in the still photograph. So Fujita was vindicated. And so the first part of his schematic model, which by the way is in almost all textbooks, really quite famous, it's been in textbook for about 50 years now, is accurate. But I wanted to revisit the second part of his hypothesis, that what was producing these cycloidal damage swaths. And by the way, before I move on to the Dodge City case, you might ask, do you ever see gouge marks? Well, actually you do. On the top, you see traditional cycloidal debris swaths. And on the bottom, you see gouge marks. And they also produce cycloidal marks. There is one subtle difference, which actually makes physical sense to me. When debris is being dragged along and gouging marks on the surface, you tend to see it bouncing along. It doesn't do it continuously. And I think that is well illustrated on the bottom. It's not very common, but this is why I took this picture at the bottom. It clearly is apparent in this case. So this is tornado number 1. And this is the one that I want to revisit, these swath marks. Turns out this is the first time mobile radar data, video, and a damage survey confirming the existence of these debris swaths have ever been collected simultaneously, as amazing as that may seem. And this tornado essentially went through dirt field after dirt field after dirt field. Here's one example. I think you see the cycloidal swaths. The white box here on the left shows the area that I'm going to analyze. I just want to remind you, this is tornado 1, and that the location of the tornado is basically due west of the radar. Hopefully that's clear in this diagram. And here is that white box enlarged. Because there's so much information in here, I'm going to enlarge this or magnify this image. So let me make sure I highlight everything. The brown dotted lines is the characteristics of the field, but I've already told you this, but I've highlighted it here anyway. Dirt field after dirt field after dirt field. The red line is the tornado center. The circles, blue circles, are the location of the tornado. The magenta circles, that's actually the funnel diameter as measured photogrammetrically. The green lines are twisted irrigation pipes, which, you know, irrigation pipes are actually pretty large. So this tornado just was so strong it mangled them. And then maybe most importantly, the white cycloidal marks. These are all the cycloidal damage swaths produced by the tornadoes. And I want to be clear that they've all been accurately plotted on this diagram, very painstakingly plotted. Here's an example. The red line represents the center of the tornado. Again, the circles represent the location of the tornado. You can see all these swath marks. It's just beautifully shown. In case you are having difficulty on the bottom, I've just highlighted those swath marks with yellow lines. I'm not going to mention what the black circles represent. Again, this is that same box. You can see those black cycloidal swath marks, the same ones you saw earlier. But what I've done here now is superimpose two images. One is the echo or radar reflectivity. Notice this high reflectivity donut and a weak echo eye. Maybe not quite as spectacular as the earlier image I showed you, but still there. And on the right, a very prominent rotational couplet centered on the track. The blue circle represents the visible debris cloud, and that was determined photogrammetrically. So again, this is tornado 1. At the time all those marks are being created, this is a picture of that tornado. So let's go to the simulations. The simulations, you saw these first three images from Dave Lewellen. Now let me show you another figure from his article. This is a recreated damage path by Dave Lewellen. The gray areas represent where dust or sand have been scoured away from the ground, and the black lines represent where it's been deposited. And I think you can see these cycloidal debris swaths. They're pretty obvious in this figure. And here is on top a picture that I took of the cycloidal swath marks. On the bottom, it's a Dave Lewellen simulation. So first off, let me talk about the observations and tell you what these dashed blue lines represent. If you look very carefully to the bottom of this, you notice there's very light colored dirt. Up here, it's very dark colored. And the reason why it's light colored is this is where dirt has been scoured away. And it does occur at a much larger area than the visible tornado core. On the bottom is Dave Lewellen's simulation, and I've transposed those blue dashed lines onto his simulations. The green and the blue represent in his simulations dirt that's being scoured away, and the red represents where the dirt is being deposited. And the comparison between the two, because these are the simulation is pretty close to the actual events of the Dodge City case, I was pretty amazed how similar they looked. But what was causing the cycloidal debris swaths in Dave Lewellen's simulations? So this may be a mouthful, but what he said was the cycloidal marks below result from deposited debris when the low-level inflow turns upward in the corner region in the updraft annulus of the tornado core. Now that may be a little hard to process, so rather than repeat it and talk about every individual word, I created a schematic model that I think does a better job. First, let me show you Fujita's model, and I already went through it, so I think it's pretty obvious. But now I created this schematic model to try to explain Dave Lewellen's model, and he was working with his student, Mike Zimmerman. It shows the vortices, but these vortices are not creating the cycloidal swath marks. In Dave Lewellen's model, what's going on, this is what he meant by the updraft annulus at the tornado core. These debris swaths are being created unrelated to these suction vortex marks. They're being created right along the tornado core. In fact, he does show in his simulations, even if these secondary vortices exist, they are not the primary mechanism for producing these swaths. And I say this with a great deal of pain because to correct Fujita's model after 50 years of existence is not something I relish, but I can't discredit the actual observations and these simulations. There are other things that buttress what I'm saying. Remember, this is the picture of the tornado when the swaths were being created, and you don't see secondary vortices. Now, it's possible that the secondary vortices are hidden inside the funnel, but at least visually, of all the pictures I took and all the movies we took, never was there a suggestion of secondary vortices. There's another reason too. Let me show you a photograph or an image I showed you before, the rotational couplet that shows you the primary tornado circulation superimposed on all these cycloidal swath marks. We took multitude of these scans through the tornado during this time. Never once was there a Doppler velocity image that even hinted that there were smaller rotational couplets associated with secondary vortices. I would have thought that somewhere along this several-minute period where we were collecting radar data, we would have seen small-scale rotational couplets. They don't exist. So there's other evidence that suggests that Dave Lewellen's model is the primary model. And let me leave you, as I wrap up, with one of Dave Lewellen's simulations. They're really remarkable. And here are these cycloidal swath marks being produced. And they're not being produced by these secondary vortices. They're being produced by the model I just showed you, but they are so pronounced. So hopefully that was a lot of food for thought. I hope it wasn't too much. And I hope I left also time for questions. So I'll turn it over to the organizers.
Professor, thank you very much for that very entertaining talk. The graphics were just spectacular, by the way.
I'll stop
We'd
sharing.
like to open the floor for questions. If you're a participant and you'd like to ask Professor a question, please click on the participants panel and you'll notice a small hand icon that you can raise. And we'll go through each question sequentially. And if you have issues, please just go ahead and enter a question into the chat and we'll take them from there and read them aloud. So, does anyone wish to start?
No questions?
We have some questions, yes.
Oh,
So
okay.
I'm going to actually read a couple that we received earlier, Professor. I have one here from George Huffman, who asks, so if wheat stems and leaves orient vertically, do any debris items that are long and thin tend to orient it vertically, say individual 2x4s?
Yeah, 2x4s would be a little harder because they have a much larger terminal velocity, so they tend to stay at the lowest levels. But 2x4s still do orient with the wind, and that's what these stems are doing. I perhaps should have emphasized that. In the center of the tornado, by the way, hi, George. In the center of the tornado, the rotational velocities are not as strong. And so what's going on? Why are they oriented vertically? It's because they're responding to either the updraft or we do know there's sometimes downdrafts in the tornado. So they are oriented with primarily the vertical motion. And so when you think about it, it's actually not too surprising that these things like wheat stems or leaves would orient in that direction.
Very interesting. And then George also follows up, Professor, and do you see time changes in the 3D radar data at various levels of the tornado that are not coincident? Or coincide,
Yeah.
I'm sorry. Yeah.
Well, if I had 2 hours, I would show you a whole sequence. I must have done 8 or 9, each radar volume. I did an analysis. And these features are not just at the times I showed you. They're persistent, if that's what your question is. They replicate time and time again. It is really interesting to see the debris cloud visually grow and how the rho HV changes with time. It is also interesting to see how this negative ZDR column evolves with time. I wished I had enough extra time to show you that evolution. So it's not a transient feature.
Understood. Professor, another really interesting question for our audience. How does global warming influence tornado activity?
Yeah, we're still debate this a lot because I don't think there's any question. We think there's going to be more thunderstorm activity, but the debate has been whether there's going to be more supercell activity. And I think we still argue about this because although there's going to be more instability and more thunderstorms, to get supercells, you need strong wind shear. And we're not sure whether the wind shear is going to also increase in the areas like in the Midwest, et cetera, equally. And so I guess court's still out whether we're actually going to get more tornadic activity.
And Professor, we also have a question asking, excuse me one second, which vertical level usually does the weak echo appear?
So the weak echo region in some cases not only starts forming at the surface, but there have been examples of the weak echo region being a coherent feature all the way up to storm top. It is amazing. That isn't too common, but at least I've seen examples of it spanning the entire thunderstorm, which means that the rotation is pretty strong all the way to the cloud top.
And then a follow-up to this, Professor. Some funnel clouds do show radar echoes at greater than 20 dBz. Does it mean the hydrometer particles are larger?
20 dB is not that strong of an echo. 20 dBz, I don't know, just a few tenths of a millimeter in diameter particles. It doesn't take too much to get 20 dBz. So I don't know if I put much into it. But remember, the one thing I do want to emphasize, when you see a funnel cloud, you're not seeing precipitation particles. You're seeing, in lots of cases, not all, you're seeing cloud. And that's what I meant where the radar can't measure that, because radars only can measure particles like precipitation and debris particles. You need a cloud radar to actually measure a funnel cloud, because you need to be able to resolve particles that are much, much, much smaller. Your typical Doppler radar doesn't do that.
Professor, what challenges do you think we have for improving tornado forecast guidance at medium to extended lead times of 4 to 14 days?
I think we're actually doing pretty well with extended forecasts. I mean, I marvel at the SPC, the Storm Prediction Center, being able to generally warn in an area several days in advance. To me, the area that we need to improve on is at the time. In other words, do we put a warning out or do we not put a warning out? We still put out a lot of false alarms. And we've not made a huge amount of progress in the last decade or so. And this is where we've sort of been stuck. And if anything, that's the area that I think we need to spend more time. The longer extended ranges, we can always improve, but I think we do pretty well already.
This is an interesting one, Professor. Could a cloud radar be deployed to observe the funnel cloud?
Yes, it can. And there have been some examples. Well, in fact, I know there have been some airborne examples of cloud radars, but not as much as you would think. Where our field is doing right now is not so much concentrating on cloud radars, although I would agree that would be fascinating. The field is really concentrating on phased array radars, where these are radars that are electronically steered, not mechanically steered. And if you asked, why do you want to do that? Well, that means you could potentially do a complete volume scan. Remember, I told you could do it up to 6 degrees in 20 seconds. Well, if these phased array radars work, you could do a complete volume scan all the way to the top of the storm in a matter of just seconds. And so that has really excited people, because at least in tornado research, we really think that's what we want. That tornado changes so rapidly. We need rapid updates on the order of seconds. We can't wait till on the order of minutes. And so that's where I think most people are focusing their attention on.
Excellent. Professor, I believe that is the questions queue. We really wish to thank you, Professor, for this nominal talk and for your time and efforts in presenting it. And also to our audience for participating. And we certainly invite you back to our next seminar in a week. So again, thank you very much, Professor Wakimoto. Really enjoyed your presentation.
Thank you so much for the invitation. I wished I could see you guys, but I'm just looking at my monitor. But again, thank you also for taking away from my day job, because it's so all-consuming. I just love it when I can do some research.
Hopefully in the near future, we'll see you in person.
Okay, take care.
Thank you, Professor.
Thank you, Professor.